This is a quick recap of standing waves. Let's say you have a string and it's tied down at both ends. You want to make a standing wave on the string. Here's a wave picture for reference. Each end is tied, so each end must be a node. Let's put a node dot right there. The first standing wave we can put on the string is to only extend to the very next node. If we stretch this shape onto the string will look like this as it vibrates up and down. The next standing wave we can put on the string, well, don't stop at this node, stop at the very next node right here. And we stretch that shape across the string. Now to make a string vibrate like this, you'd have to pluck it with 2 fingers. You'd have to pull one finger up and pull the other finger down, and then let go. Now let's make the third standing wave that fits on the string. Instead of stopping at this node, stop at the very next node, and stretch that shape across the string. The string's length from one end to the next is L. So let's figure out how many wavelengths, or how many cycles, fit on the string for each standing wave. In the first case, we go up, but we don't have a trough, so this is half of a cycle. L is equal to 1 lambda over 2. In the second case, we go up and then we go down. We have a peak and a trough. This is a full cycle. So the length from one end to the next is also equal to the wavelength. We can write wavelength by multiplying it by 2 over 2, and we haven't changed the fact that L equals lambda. In the third case, we go up to a peak, we have a trough, a valley, and then another peak. So we have one full cycle right here, plus another half cycle. L equals 3 lambda over 2. Now if we compare the formulas, the numerator value counts up 1, 2, 3. Let's just call that number n, and the formula becomes L equals n lambda over 2, where n counts up 1, 2, 3. Okay, now let's take a pipe of air, and the air molecules vibrate left and right. They can produce standing waves inside the pipe. And just like before, we're going to draw the first 3 standing waves that we can put into the pipe. Okay, what are the boundary conditions? Is this a node or an antinode? Is this a node or an antinode? Both ends are nodes because they both are free ends. The air is free to move back and forth because the end is open. Okay, so we have to start at an antinode and we have to end at an antinode. So the first wave we can put is just this shape, stretched out. Now for the second wave, instead of stopping at this antinode, we could stop at this antinode and stretch that shape across the pipe. Finally, instead of going to the second antinode, we can go to the third, and we can stretch that shape out across the pipe. Okay, the length of the pipe is L. We want to figure out how many cycles have we fit into each pipe. Well, for the first standing wave, we go from peak to trough, but we don't go back up. So this is half a cycle. For the second standing wave, we start at a peak and we return. So we've got 1 full cycle. And instead of saying that L equals lambda, we're going to write that as L equals 2 over 2 lambda. For the third standing wave, we have 1 full cycle here, if you follow my mouse, and then we go from peak to trough. That's another half cycle. So we have L equals 3 halves lambda. If we compare the formulas, again we count up 1, 2, 3 in the numerator. Let's just call that value n, and now the equation is L equals n times lambda over 2. And we're counting up for n, it is 1 and then 2, and then in the bottom picture, n was 3. Finally, as our last example, we have a pipe, and we're going to do this 3 times, but instead of being open at both ends, it is closed at this left edge. So what are the boundary conditions? Well, let's see. Air that's up against this closed end, that air can't move, it can't vibrate, because as soon as it tries to start moving, it bumps into the wall, and the wall prevents its motion. So we have a closed end and an open end. Therefore, we have a node right here and an antinode right here. So here's my reference wave. We have to start at a node, and we have to end at an antinode. So for our first standing wave, let's stretch that shape into the pipe. For the next standing wave, don't end at this antinode, end at this one, and stretch that shape into the pipe. We go up and then down. Finally, instead of ending at this antinode, end it at this antinode. And so we go up, down, up. There's the shape. Again, the length of the pipe is L. So now I want to figure out how many cycles fit into each pipe. Every time you go from a node to an antinode, that's 1/4 of a cycle. So in this first case, L is just 1/4 lambda. In the second case, we go from node to antinode, that's 1/4. Here's another 1/4 as we go back to the node. And then here's a third 1/4 as we go back to an antinode. So L is 3/4 lambda. Here, we have 1/4 node to antinode, then a second 1/4 node to antinode, a third 1/4 node to antinode, a fourth 1/4 node to antinode, and a fifth 1/4 node to antinode. If we compare the three formulas, the numerator counts up 1, 3, 5. It skips the even numbers. So let's call that value n, and the formula is L equals n times lambda divided by 4. And again, n is counting up 1, 3, and 5. So what do we notice? These two have the same formula, and n is any number you want, any positive integer. This one had a different formula, and n was only the odd integers. Okay, final recap. Why are there two different equations? Because it depends on whether the two ends of the medium have the same boundary condition. Is the rope tied down at both ends, or is one of the ends free to move up and down on the rope? And then the other scenario we have is just that. The two ends could have different boundary conditions, like the pipe, where one end was closed off by a wall and the other end was open. So here are the equations from the last page, but there's something we have to fix. There are lots of different wavelengths. All of those waves we just drew in the pictures, they weren't all the same wavelength. Some were really stretched out and some were kind of scrunched together. So the different wavelengths we can produce, we call those the lambda n values. So we use a subscript here. We call them lambda 1, lambda 2 for the second wavelength, lambda 3 for the third one in our picture. And sometimes we'll multiply, cross multiply, to get this equation. And sometimes we'll rearrange again, divide by n, to get this equation. Now, these are all the same equation. You have to memorize one of these forms, but you get to choose which one you like to memorize. I personally kind of like the second one, because it's easy to remember the left side, n lambda n lambda n. It's kind of easy to remember. And then on the right side, that's what changes for the two different scenarios, 2L versus 4L. The other thing you have to remember is that the value of n is any positive integer when the boundary conditions are the same, and it's only odd integers when the boundary conditions are different. So this is how we find the value of lambda, which fits inside the pipe. We call those the harmonic standing waves, or the harmonic frequencies. But we haven't written frequency anywhere, so how do we find the actual frequency of the standing waves that satisfy the boundary conditions? To find the frequency, you have to use the wave speed equation. And the first frequency, that's what you get when you plug in the first lambda. The second frequency, that's what you get when you plug into this formula, lambda 2. So that's how you find the harmonic frequencies, or the frequencies that can produce standing waves in some medium.